So a big, big, big applause for Mateus Guimarães.
So today we're going to talk a little bit about modular monoliths. Modular monoliths have recently come to rise again, and people are talking about them quite frequently. And they are super, super interesting. Before that, a little bit about me. So I'm a software developer. I'm also an educator. I do powerlifting, I do photography, content creation, spend time with my wife. This is my YouTube channel. You might find some lessons there on Laravel internals, software architecture, that kind of stuff. I also do powerlifting, as Kaneko said, so there are some videos on myself as well. This is me and my wife at Disney. My wife is here with my mom, actually. I don't know where they are exactly, but they're at the audience, so that's pretty cool. Thank you. But we're not here to talk about me. We're here to talk about software architecture and modular monoliths. So before we talk about modular monoliths, we got to talk about what a monolith is. And a monolith is probably what most of us use at work. It's our regular applications, our desktop applications. It's one big application, one artifact. Everyone knows then we use regular method calls to communicate between components in the application. We have database transactions, and we're going to talk about them really soon and why they're so important and we don't value them. And usually we only have one artifact. So they're easy to deploy, they're easy to scale as a single unit, but they also have their problems. The biggest problem is probably tight coupling between components. You have no well-defined boundaries. You don't know where component starts and where it ends. If you have a big project, a medium to large project, it gets really hard to understand. You join a new project and you have this huge repo with 700 files. There's a lot of cognitive load. This is what a monolith usually looks like. You can see that we have different components talking to one another, and they're grouped by color just so you can identify whether they belong to the same module. So here's the thing about a monolith. Even if you have all of these components talking to each other, stumbling on each other's toes, you can still say, okay, this is part of the product module. This is part of the shipping module. They're all spread throughout the application, but you still can define them. You can say, okay, this relates to shipping, this relates to the warehouse system, and you can tag them, if you will. Now, this is what you usually end up with in medium to large applications. We call this a big ball of mud. It is a complicated, monolithic application. You have tight coupling between components. It is hard to understand. You touch feature A, you break feature B. On the other hand, another common architectural pattern is microservices. And microservices have some benefits. They're easier to scale individually, they have well-defined boundaries, and they're resilient. So if microservices A breaks, all the other ones are still going to work, right? They do have lots of trade-offs. So you have multiple repos, you have a much more complex infrastructure. What was previously method calls turns into network calls, and you guys know that you cannot trust the network. It is more complex by default. You have to deal with consistency, so we have database transactions in monolithic applications. You don't have them in microservices. You need to do compensatory events. You need to do sagas, for example. And they're much harder to debug just because you have multiple applications. So the infrastructure itself is more complex. This is what a microservices-driven application kind of looks like. So you have those boundaries, you have multiple databases usually, and you communicate through the network. Now, the interesting thing is you can see that with microservices, you are obligated to think about boundaries because it cannot work otherwise. The shipping service does not know of the data on the product service or the warehouse service. You're physically separated from those services. So you're obligated to think about those boundaries and how your services communicate to one another. A middle ground between those is the modular monolith. So although on a microservices, we do have this separation, this clear separation between boundaries, it is not exclusive of a microservices-driven approach. It is required, yes. You don't have to do this in a monolithic application, but it's not exclusive. And you can apply that, whoops, how do I go back? Sorry. I thought I was going back. You don't have to apply that to a monolithic application. With a modular monolith, you kind of have a middle ground. So you still have one artifact, you still have one repo, you still have one deployment unit. you have a simple infrastructure. You can have multiple databases, but you can also have one single database. You get database transactions back, so you no longer need compensatory events. Well, you can if you want to, or if you have event-driven communication, we're going to talk about that. But you can have everything in a database transaction, and that's amazing for consistency. And instead of having those physical boundaries, you have what we call logical boundaries. Within a modular monolith, we want to have independent modules. We want to allow teams to work independently in different modules without affecting one another. And we want to have low coupling between those components. So this is what a modular monolith looks like. You can have multiple databases, but in this example, we have one. We separated those boundaries between method calls. You can also do events, and we're going to talk about that. But this is what we call a logical boundary. You're not physically separated between services. They can talk to each other. If you want to, you can do a method call to another service. It is going to work. It is an option. So talking about coupling, who here has worked on feature A? You thought that was good, and you broke feature B? Raise your hands. Okay. Yeah, me too. So what is the reason for that? Does anyone know? Coupling. Okay, cool. Coupling. Yeah, so when you have tight coupling between components, it means that when you change one component and you have an object graph, you can affect other components in that object graph. So you touch feature A, you deploy, and this happens, right? And you have to roll back, and it's a mess. We want to tackle that with modularization. It's one of the things we want to tackle. So in a modular application, we definitely want the modules to be somewhat independent. And the thing about coupling is it's not 0 or 1. It's not you're either tightly coupled or you're loosely coupled. It's a spectrum. You can have some pieces of the application that are more coupled to some other pieces, and you can have certain pieces that are pretty isolated. So let's say that you have a system that deals with payments. You probably want the payment piece to be somewhat isolated. Maybe that's your core business. You want to give this a little bit more attention. You want to give it a little bit more interaction, right? We want to empower teams to work in parallel between different features without affecting one another, just like you have in microservices. That's a huge benefit from microservices that we can have in modular applications. And with modularity, you decrease the surface area that a component reaches. You decrease the blast radius of changes, so they're concentrated in a single place of your application. So this is an image from a talk on YouTube. There's a source there. It's a great talk. You should watch it. The big difference between monoliths and microservices really is the number of deployment units. It's not the databases. It is the communication to some extent. You can still do network calls on monolithic applications. But the big difference is deployment units. And with a modular monolith, we still have one deployment unit, but you can think of as a big application with smaller applications inside communicating to one another, versus with microservices, multiple applications orchestrated to communicate with one another. So the first step to modularization is code organization. And I want to add a few remarks here. This is not a domain-driven design talk. I don't want the Dutch to go after me. They can go after Daniel. This is not a talk about decoupling from the framework. You can be super coupled to the framework. It doesn't have anything to do about that. It is about coupling between your components inside your application. And this is not a recipe. I don't want you to watch this talk and think this is a recipe you can just apply to your projects. I want to give architectural ideas that you can use when you see a problem that fits those needs. So code organization. We have two types of, mostly, organization. You have what Bobby spoke about yesterday, grouping by color or by type, where you have your models together, your mailables together, your controllers together, etc. And you have grouping by context. So you group everything in a single context. Let's say that you have a shipment service, everything is inside shipment. Now, this is not following the framework conventions. You can still follow the framework conventions inside your modules, and you can treat it as a mini Laravel application, or you can choose not to, and we're going to talk about that as well. So you have grouping by type, like I said, and you have grouping by context. And you can think of the context as, some people are going to call it modules, some people are going to call it domains, features, context. You can have context within context, those are subcontexts. And let's talk about grouping by type real quick. So imagine that you have a few models, right? You have payment, support ticket, site template, and shipment. Why are they together? What do they have in common? They're models, right? And then you go and you have some actions or jobs or commands, whatever you want to call them. Why are they together? Because they're actions. This is just a provocation. Does it make sense for them to be together? I don't know, maybe. Another thing you can do is to group them by context. So you have an action with a model, and obviously in a real application, you'd have many more components, and they're grouped by their context. So you have a payment with a refund payment action, a site template with a refresh site template action, that kind of thing. This is an example of what a module might look like. This doesn't look like a regular Laravel application. This is what we call vertical slices. So you slice a feature, and you get everything together in a single folder. Another option that you can do is the regular Laravel structure. You can have that inside your modules, just like your regular Laravel applications. You don't have to change anything. This is Symfony. You can see that it looks modularized, right? You have several components. They talk to one another, maybe, sometimes through an event bus. This is Laravel. It also looks pretty modularized to me. You have different components. They talk to one another. They deal with coupling. They have that in mind. How do I do this in a Laravel application? Well, the first step is you can do this in your app namespace if you want to. I prefer to add a separate namespace. You can go into your composer.json file and add a new namespace. It can be modules, it can be domains, whatever you want. The folder can be modules, source, that's up to you. And you can start from there. The most interesting thing to me isn't the code organization, because I think that's pretty subjective. If you want to have a regular Laravel application grouped by type, that's completely fine. You can still have those things in mind. The most important thing to me are boundaries. So how do your components communicate to one another? Where does a component start, and where does a component end? Let's talk about Stripe. Whenever you call an API like Stripe, you have a request and a response, right? When we think about contracts, we usually think about interfaces, right? But that's not the only thing a contract is. If you think about the Stripe endpoint, it is a contract. You have an input is expectation, and you have an output expectation. And Stripe offers both. So the provider offers you a contract. It tells you, okay, we expect to receive this, and we're going to give you this. That is a contract, and you accept that contract. You have to fulfill Stripe's requirements, otherwise the API is not going to work. Let's look at a very simple example. Let's say that you have a user class, really simple. You have a token user class that does some magic and then issues a token. You also have a contract. So you expect an input, you expect an output, and the consumer knows about that. So the provider is giving you that contract, and then consumer is fulfilling it. So the provider offers a contract. The consumer has to respect that contract. And you can see that throughout the Laravel framework as well. You have components offering contracts, and you have other components consuming those contracts. So we go to something called cross-boundary communication. And I know this sounds really fancy. It isn't. It's just communicating between boundaries. So how do you communicate between component A to component B? Let's look at a few examples. So if we imagine each component as a square, the way I like to think about that is you have a square. You have a box. You define whether that is a black box or a white box, whether the internal implementation is going to be known by other boxes or not. The way I like to think about that is you have the center of the box, which is your internal API, and at the border you have your public API, which is just like Stripe. Stripe offers a public API, right? You don't know what's going on inside Stripe. You make a call to their endpoint. You don't know which models they have, which jobs they're executing. You just know that you pass some input and you get some output back. And that's how I like to think about modules. You have implementations internally at the module, and you have those contracts or translators or whatever you want to call them at the border, and they're responsible for representing the module's public API. Again, coupling is a spectrum, so you don't have to follow this to the rule. You can change things. You can see what fits your project. But it's good to have this in mind. And then you have a consumer, a producer, and then you have the consumer consuming something the producer offers. So you have your public API at the border, and you have your internal hidden API at the core of the module. Some useful guidelines. With modules, we want at the very least some organization, and we covered that with code organization. That's the simplest part. But we also want modules to have some independence. If we do all of that, and we don't think about independence, we're just giving up a lot of the benefits we can have with modularization. As a rule of thumb, theoretically, modules should not know about other modules' internals, because you're violating the contract, you're violating encapsulation. Sometimes you don't have that big of a problem, and it's just easier to do that, and you can go with that. It's fine. It happens. And you want incoming messages to a module to be transformed into something that's meaningful to that module's domain. So you want the producer to also own the objects that are going to go inside it, usually. Or you can have specific objects that are meant to be passed around. So we're going to talk about data transfer objects. Sounds fancy, it isn't. It's just a bag of data. It's an object that is meant to be passed around. That's why it's called a data transfer object. And we can use those to pass information between modules. The thing with DTOs is they represent a contract. So you might think, okay, why can't I use an array if I just have a simple object like this? Because you don't have types, and you have no guarantees that the array is going to match what you expect, right? And you can fail early unless you do lots of checks and it gets really complicated. So this is an object that's meant to be passed around. This is an example of an object. I have a pending payment, which is going to be passed to a payment service, which is going to then process the payment. And the payment service knows what to expect. That's the beauty of it. The consumer knows what they have to send, and the producer knows what they're receiving. So let's take a look at some code. I don't know if you can look that way all the way to the back, but you have a relatively simple controller here, and I know it's messy. We're going to refactor it. So you have an order, you're creating an order, you add in some items to the order lines, you're decreasing the stock of the product, you're saving the order, you're processing the payment, et cetera, et cetera, et cetera. See how many different modules we're touching in a single controller. So we're touching something that relates to cart items, probably product. We're touching orders. We're touching stock management. We are touching payments. We're touching payment providers and payments. We're touching shipment. So we have a lot of cross-boundary communication here. Even if your application isn't modularized, you still have that. They still exist. You can still determine them. So we can refactor this a little bit, and we can maybe create an action called, fetch cart item by product IDs and purchase items, and you kind of encapsulated that into another class, and it's more readable, right? But if you go into that class, you still have the same problem. You still have a lot of boundaries being touched. So you're still decrementing the stock, you're still making a payment, creating a shipment. And as you can see, there's a lot of data modeling going here. There's not a lot of intent. You're saying create a shipment. You're not saying start the shipment for this order. You're creating a record in the database. A way we can make this a little bit more digestible for our different modules is, and this is what we have on the purchase items class, by the way. So you have the class, you abstract that into a class, but it still holds all of the data. We can do something like that. So we can encapsulate that into some services owned by the different modules. And you might look at me and say, okay, you're just stupid because you added those services, but they just do the same thing. And that's the thing. As an application grows, complexity also grows. And our models have to change. So whereas we were just creating a shipment back then, in the future you probably have much more complicated shipment logic. You might be shipping to different stores, you might be using different providers. So it's very likely that it's not just one shipment model and that's it. You have more complicated logic. And what we're doing here is we are modeling behavior. So we're no longer creating a shipment record on the shipment table. We're saying start a shipment for this order, pay this order, and you have well-established contracts. One of the problems, and whenever I say problem, I don't mean literally a problem, but something that could affect you here is you still have a lot of coupling between components because these components know about each other. So if you were to break something in the payment service, what would happen to this code? It would crash. If you were to break something on the shipment service, it would crash. And this is what we kind of have. So we have those services being owned by the different modules, But purchase items still knows about all of the modules. So you're still somewhat coupled to them. And if something breaks there, it's going to break your code. What can we do to remedy this? Well, we can do event-driven communication. So instead of talking to these modules directly, we can talk to a bus. So instead of me going to James and saying, hey, James, take this message, I can go to Kanako and say, hey, Kanako, can you deliver this message to James, to Tim, to Joe? And Kanako is going to deliver it to all of them. And I don't know about it. I mean, I just give it to Kanako. Kanako decides who he wants to give it to. So it will look something like this. Instead of talking directly to these modules, we could dispatch a message, an event. And this message says, OK, an order was placed. And then everyone who's interested in doing something once an order is placed is going to listen to that event. And now the consumer doesn't exist. You only have a producer. You have someone dispatching an event, and then you have a bunch of other modules listening to that event and doing something with that, and you no longer have direct coupling between these components. If the shipment service, for some reason, isn't working, that's fine. The order is still going to be placed. If the payment service is broken, sure, the order won't change state into paid, but it's still going to be placed. And you can fix it and apply it to all of the pending orders. Let's say that your boss says, OK, we want to give a reward to everyone that purchases over $500. Instead of you adding some code to a class synchronously, you can just add a new listener. The event's already there. You don't have to do a lot of things. You just add a new listener, and you can add functionality ad hoc. So you also have that benefit. Now, if you look at this, you can have different teams or different people working in different modules. And since they know about their API, they know about the events that are being placed, they can work independently. They can run their own tasks. They don't have to touch the purchase items class if they want to, for example, task that an order is going to be paid or shipped or that a reward is going to be given, because they have the event. And the event's just a DTO. It's just a bag of data. Let's look at an example. So what if we have a purchase items class, and all it does is add some lines to the order, and then dispatch an event saying an order was placed, that's all. It doesn't deal with payments. It doesn't deal with shipment. Amazon does this. So if you purchase something at Amazon, you might notice that your card isn't charged right away. Your order goes through, and then at some point, your card is processed in the background, and it might fail. And you get an email saying, hey, your payment failed. So you dispatch an event, and then you can, in the pay order, for example, you can listen to that event. So you listen to order place event, and then you can do something with it. OK, so an order was placed. I probably want to try and charge the user's card. And if it succeeds, you can dispatch a payment succeeded event. If it fails, you can dispatch a payment failed event. So with event-driven communication, you kind of go back to what we said about microservices. You need compensatory events because it's no longer synchronous. You have eventual consistency. And then you can have a fulfill order class that listens to that payment succeeded event to fulfill the order. You might have a start shipment for order class that listens again to the payment succeeded event to start shipment. And then you might have, let's say, a decreased product stock that listens to payment succeeded to decrease the stock of a product. In real life, you probably want to decrease the stock as soon as they make the purchase so that you don't have multiple people buying something out of stock. What are the trade-offs? Well, you create another layer of interaction, so you can no longer look at a block of code and know everything it does, because it's not there, it's somewhere else. You have eventual consistency if you have few listeners, which I would recommend. That is, at the point an action happens, the database might not be, the changes might not have been applied yet. The listeners might not have been executed yet. So you have to take that into account. So for example, if you're in e-commerce, you have to expect that by the time the user completes their order, they might not have paid for it yet. They have not necessarily paid for it. You need compensatory events. So if the payment fails, you have to dispatch a payment fail event. If it succeeds, you have to dispatch a payment succeeded event. And again, because of the layer of interaction, it's harder to reason about everything a block of code does. We're running out of time, but real quick. One important piece of modularization is data ownership. Let's look at an example. Let's say that you have your application, and you have one separate module, this learning module, and you have a course and lessons. And can a user access a given course? That's a simple question, right? You want to make sure they can access a course. And this is how it is often modeled. You have, does the user have an order that has an order item that is a product that the course is attached to? So you're touching a lot of boundaries to determine something. And you're licking your module's concerns. So it often looks like this. The user has an order, the order has an order item that has a product, that has a course, right? What would be a simpler way to do this? Well, you could publish a product purchase event, and then you could have the learning module listen to that and say, okay, someone purchased a product, I'm going to unlock the courses related to the product. And then you can have a relationship between courses and products, probably belongs to many. So you still have relationships between modules, right? But you still have independence. If the app doesn't exist, nothing changes in the learning module, and vice versa. You can go a little bit further. So you still have a user-to-course relationship, right? So if the user model is gone, your learning module breaks. Your user model is probably not going to be gone, but sometimes you have to do this in other modules. So what you can do is you can introduce context-specific entities or models. So what if you had a student model inside the learning module that has courses instead of a user having courses? That gives you a much smaller API. Who here has ended up with a God user object? That user object that has 30,000 relationships, 30,000 methods, 30,000 accessors. And this is not just for users. I'm just using users as an example. You can get a much cleaner API, a much more concise API, and a much smaller surface area. Now, it does come with trade-offs. Now, you have to listen to an event. You have to have a student record, for example, to unlock the course for that student. But you no longer depend on data from a different module. All of the module's data is contained inside it, so it can work in isolation. Imagine that you're creating a package inside your application and you plan to open source it later. What happens if you create the package in a separate namespace, but you still have calls through a Laravel application, direct calls? You won't be able to open source it because it won't work in isolation. So can a student access this course simply becomes, does the student have the course unlocked? And that's it. This is an example of a real-life application that has no subcontext. And the trick with this is you're kind of obligated to keep your context small and to keep your API very concise. So you end up organically creating those new models and new subcontexts and whatnot. Modularization encourages you to actively think about your systems and their relationships. So that's an unrelated thing that is really good with modularization. That is, you have to take a step back and think about your components and boundaries, and that gives you a little bit more time to think about how your systems going to interact, how your systems are going to interact with one another. Sometimes when you're dealing with monoliths, we just keep creating models and controllers and listeners. It's super quick, it's super easy. So sometimes we just kind of do it without thinking too much. And obviously this is a side effect because it's slower and because you have to think about those things, but it gives you those benefits. All right, so let's recap. The first thing we do is to split our application in different modules. Even if they do not exist in your directories, you can think about them, right? You can still think about them. The second thing we do is to enable a public API for each one of them. Then we start to communicate between the internals of a module to the public API of another. So implementation to contract, implementation to contract. We never want the internals of a module to talk to the internals of a different module. And this is pretty much what it looks like. Another option is to, instead of having that communication, we can dispatch an event, right? We dispatch an event, and then the other modules can listen to it. The other components of your application can listen to it. And there you have much less coupling because you don't know about the other components. You know about the event bus, you know about the event itself, your DTO, but you don't know about anything else. So, some suggestions. Coupling inside the module is much less concerning than coupling between modules. So, if you have your module and things are tightly coupled, that's probably fine. It's still within the module. You're still going to deploy that, together frequently. If you have coupling between modules, then it becomes a little bit more problematic because you can run into those situations we talked about earlier. Within your modules, always try to expose a very small, as small as possible, of a public API. And modules allow you to use different solutions to different problems. So you might have some components that are more complex intrinsically. So if you're in e-commerce, payment is definitely complex, shipment must be complex, and you can use more complex solutions for those problems and keep other modules, simpler. To apply modules to Laravel, the first thing we want to do is to probably have a modules namespace, or whatever you want to call it, to group them. We want to leverage service providers to load routes, configuration files, and that kind of goes against what Taylor said yesterday. We don't want to use service providers, or we don't have to. But if you're doing modules, you probably want to have everything related to the module, in its box. You don't want it leaking outside the box. We should think about whether a module should hold all of its data. Sometimes it doesn't have to. Sometimes we have simple modules, and that's fine. And we usually, okay. Testing. All right, thank you. I'm right now. All right, cool. Is it working? Okay, cool. And sometimes we also want to leverage the event bus to pass messages to different modules. Some packages real quick. We have Laravel modules, which is the most popular one. David is actually at the audience right now, I think. We have Internachi modular, which I think Daniel worked on with Chris Morel. And one of the trade-offs that going with the modules is you can no longer use scaffolding commands by default or auto-discovery, and these packages will give you that back, so you can use auto-discovery within modules using those packages. And you can also use depth track and pass architectural tests to define your boundaries and have, for example, your tests fail if you're crossing a boundary you shouldn't. So I suggest you look at those. Some good articles, and I'm going to have the slides published later, but Shopify has a really good article about modularizing their monolith. There's a good book called Strategic Monoliths and Microservices. There's a RailsConf talk, really good as well, and a little bit more hardcore than mine, that you should check out. And also my Laracast course, Modular Laravel, which is available on Laracasts. So you can also check that out to have a little bit of a deeper vision on this. And also, I did a podcast with Chris Morel, who was mentioned yesterday by Daniel as well, about modularization, and we have very different opinions, so you can also check that out. And that's pretty much all. So, thank you.
I should have invited you to hold the mic for Taylor.
Oh, yeah, for sure.
You got a bigger arm than me. You can hold it better. So I got a couple of questions.
Okay.
So first, Jose Manuel Cardona.
Okay.
You got here at least a Hispanic person. How do you scale the monolith?
You can scale it as a regular monolith, just either vertical or horizontal scaling. You can also apply reverse proxies to direct traffic to specific modules based on the endpoints, which is a little bit more complex. It's definitely not as easy to scale individually as a microservices architecture. You can still do it, but you're still loading the entire application in memory, regardless of whether direct traffic or not. So in general, just like a regular application.
Thank you. Martin is asking one thing. I'm going to answer myself. He's asking, can Mateus deadlift Kaneko? I'm saying no. Okay? That will settle.
Okay.
And the anonymous user is asking, did your wife enjoy your talk?
I sure hope so. I mean, I don't know if she understood much, but I hope she enjoyed it.
Did you enjoy it? Sí.
She's shy. She's shy.
A big applause for Mateus.
Thank you.